Section 4-6 is on differentiability and continuity. And the objective of this section is to show that a function is continuous by showing that the function is differentiable. So if you recall what we've studied so far in this chapter, we actually completed our rules for derivatives that we need to know. We talked about the product rule, which is used to find the derivative of a product of functions. We talked about the quotient rule, which is used to find the derivative of a quotient of functions. We also talked about the rules for the derivatives of all 6 of our trig functions. And finally, in the last section, we talked about the rules for the derivatives of all 6 of our inverse trig functions. And that actually rounded up for us, or finished off, the rules for derivatives that we need to know. And so now is a good time to look back at this connection between differentiability and continuity. Now that we know all the rules for derivatives, or how to differentiate, we can look at this connection. And if you recall back in Chapter 2, we defined exactly what continuity meant. Continuity meant there were 3 parts to this definition. It meant, first of all, continuity at x equals c meant that f of c exists. Secondly, it meant that the limit as x goes to c of f of c exists. And finally, the third part was that those two had to equal each other. So the function had to exist, the limit had to exist, and both of those had to be equal to each other. And it turns out there's a nice connection here between differentiability and continuity, and that's what we're going to take a look at. And to some extent, sometimes working with derivatives is a little bit easier than working with that definition of continuity, and vice versa. Sometimes looking at the definition of continuity tells a little bit about differentiability. So let's take a look at, first of all, the definition of differentiability. There's actually 3 definitions here that we're going to look at that deal with differentiability. The first one is for differentiability at a point. And we say that f of x is differentiable at x equals c if and only if f prime of c exists. And what we mean by that is that f prime of c is a real number. If you recall in that definition of continuity, we say that f of c has to exist in that first part of the definition. And what does that mean? It means that when you plug in a number c into your function, you get some number out. F of c exists. And the same definition here is applying to this definition of differentiability. That is, when we say f prime of c exists, all that means is you can take the derivative function and plug in some number c, and you get a number out. If that happens, then you're differentiable at that point. If this thing's undefined, then you're not differentiable at that point. All right, let's extend that a little bit to differentiability on an interval. So the definition here is f of x is differentiable on an interval if and only if f of x is differentiable for every x value in the interval. So in other words, the derivative has to exist on the entire interval, which means that you have to be able to plug in every single point on that interval and get some number out. So that's differentiability on an interval. And finally, the last definition here is just talking about an entire function. And we say that as far as differentiability is concerned, f of x is differentiable if and only if f of x is differentiable for every x value in its domain. So in other words, you have to be able to find the derivative and plug in a point for every single point on its domain in order to be differentiable. Many functions that we work with are differentiable at every single point. All of our polynomials we've studied so far, our exponential functions, those are all differentiable. Our logarithmic functions, etc. A lot of functions have that property, that they're differentiable at every point, but there are still some functions out there that don't have this property. All right, one thing to note here about differentiability, and the book mentioned this same thing here, so I want to make sure that I clearly point it out to you, and I'll draw a picture here to help illustrate this in a second. But the note says this: if f of x is defined on a closed interval from a to b, closed interval, remember again, means that we're including the endpoints. So that's all the values between a and b, including a and b, and we use square brackets for that. So if f of x is defined on a closed interval, then it can be differentiable only on the open interval. And the open interval means that we are not including the endpoint, so that's all values of all values between a and b, but not a and b. And we use parentheses to illustrate that. And that's because the limit does not exist at the endpoint. And I know we're talking about differentiability here, and you might wonder, well, where does limit come in? Well, remember the definition of a derivative is based off of a limit. It's a limit of a difference quotient. So that's the limit we're talking about. The limit does not exist at the endpoint, and that is because only the one-sided limit actually exists at an endpoint. That is, I can only approach that point, that endpoint, from one side or the other. From the other side, it's not part of the interval that I'm working with. So let me illustrate this with a little sketch to help explain what we mean by this. Let's say that we've got some function here. Doesn't matter really what our function looks like, but we'll give it a little bit of a curve here. And I'm going to go ahead and mark a point here as an endpoint. Let's just say we've got a function that looks like this. And we'll say that this is at A, and this is at B. Again, the problem with limits here, you can see that as I approach A, I can approach A from the right-hand side, but I cannot approach A from the left-hand side. There is no function over here, so I can't approach from this direction. I'll draw an arrow there, but there's no function to follow to get to that point. And the same thing happens over here at B, except it's the other way around, that I can approach B from the left-hand side. I can follow the function as I approach B from the left side. But over on the right-hand side, there's no function over here. So again, I can't approach from the right-hand side. So I run into a problem here at these 2 points that, there is no left-handed limit on as I approach A, and there is no right-handed limit as I approach B. And again, if you look at the definition of what a derivative is, let's take A for example. F prime of A would be defined as, remember your definition here, it's the limit as x approaches A of f of x minus f of A all over x minus A. And again, so that's the limit of a slope. It's a limit of a difference quotient there I know we're talking about. But the fact that the function doesn't even exist on the left side of A means that the left-sided limit of this is not going to be the same as the right-sided limit. So therefore, this limit cannot exist. The same problem exists, of course, at B, except f prime of B is the limit as x goes to B of f of x minus f of B all over x minus B. Okay, we defined that initially back in chapter 3 using f prime of c, but I'm just defining it at these endpoints to illustrate this problem. All right, so what that tells me then is anytime I take a derivative, just realize if I have an endpoint there, I lose the endpoints as part of my derivative. Okay, I keep every point in between, but because of this little issue here, we technically lose our endpoints. All right, so here's the property that this section deals with. And it says the following. It says, if f of x is differentiable at x equals c, then f of x is continuous at x equals c. In fact, many times we read this off as differentiability implies continuity. In other words, if you have differentiability, then you automatically have continuity with it. If f of x is continuous, or excuse me, if f of x is differentiable at x equals c, then f of x is continuous at x equals c. That's our property. And so instead of having to go through the 3 parts of the definition of continuity to show something's continuous, which sometimes can be a little bit of trouble to show that, instead, what I can do is find a derivative of a function and evaluate it at c, thus showing that it's differentiable at c, and I automatically get continuity with it. So instead of showing continuity, I really show differentiability. I use this property then to pull in the fact that it must also be continuous there. And again, the way that we commonly read this off is that differentiability implies continuity. This is a nice way to help us remember that property. Differentiability implies continuity. And make sure you get that property right, because if you read it off the other way, it's not true. Now here's the contrapositive, if you remember, with a theorem that's in the form if P then Q, P and Q being the condition or the hypothesis is the P part and the Q part is your conclusion part. Remember, you can rewrite that from geometry. You saw how you could rewrite that several different ways. You can write if P then Q, or you can write if Q then P, and if not P then not Q, and if not Q then not P, and so forth. So there's 4 different ways you could write this statement. And this form of it is what we call the contrapositive. And the contrapositive is where you take the hypothesis and your conclusion and you swap those two, and you take the opposite of them. Turns out for any theorem that that you have, or any property that we have that's in the form of if-then, the contrapositive is always true. All right, no matter what the theorem is, it's always true. So it says, I should say, if the theorem's true, then obviously the contrapositive is true. If the theorem is false to start off with, then obviously I can't guarantee the contrapositive is going to be true. But here's the property. It says if f of x is not continuous, so that's the opposite of our conclusion up above. It's not continuous. It's discontinuous at x equals c. Then f of x is not differentiability at x equals c. So if you don't have continuity, then you can't have differentiability. If you're not continuous, then you're not differentiable. Now again, don't read too much into these if-then theorems. You can't say, well, if I don't have differentiability, then I must not have continuity. That's not what this says. It just says if you're not continuous, then you know you're not differentiable, and that's it. Okay? So let's see if we can use this theorem or these two properties really to help us answer a few questions. Let's take a look at example 1 there on page 155. It says, prove that f of x, let me write down this function here, f of x is equal to x squared minus 7x plus 13. And they want us to prove that it's continuous at x equals 4. I'll put it as a question there. Is it continuous there at x equals 4 is really the question we want to answer. They said prove that it is, so it must obviously be continuous. We just are going to prove it. Now again, one way that you could prove this is to go back to our definition of continuity, show that the function exists at 4, show that the limit exists at 4, and then show that those two are equal to each other, and you'd be done. All right, but a function like this is pretty easy to take the derivative of. Polynomials, we're getting pretty good at taking derivatives of these guys. Derivative of x squared is 2x. Derivative of 7x is a minus 7. And of course, the derivative of 13 there is 0. So the derivative of this is 2x minus 7. And I can plug in 4 into that pretty easily. 2 times 4 is 8, minus 1, or minus 7 is 1. So this function is differentiable at x equals 4. Again, differentiability just simply means that I can plug in a value into the derivative and I get a number out. And that's what I have here. I plugged in 4 into the derivative and I got a value of 1 out. So I can conclude that this function is differentiable at x equals 4. And thus, from my property, it must also be continuous at x equals 4. Thus, f of x is differentiable, I'll abbreviate that, at x equals 4. And therefore, f of x is continuous, I'll abbreviate that as well, at x equals 4. Differentiability implies continuity. If I can show that my function is differentiable at a point, I automatically get continuity with it. All right, so that's using that first property we looked at. Let's take a look at another example. Look at example 2. This one says, is the function g of x, let's go ahead and write down this function. G of x is equal to x minus 2 times x plus 3 all over x minus 2. Is it differentiable at x equals 2? So this is a different question here. Differentiable at x equals 2 is the question in this case. Now again, we could go through and find the derivative of this. Remember, differentiable just simply means that I can find the derivative and plug in a point and get a number out. But however, when I look at this thing, I've got, product rule in the numerator and it's quotient. It's going to be a little bit of work for me to find the derivative of this thing because I got to follow both quotient rule first of all, and then secondly, product rule in that numerator. Yeah, written in this form, that's what I'd have to do. You could, of course, multiply the numerator out there and then not have to follow a product rule. You just have a polynomial there. But nonetheless, I'd have a little bit of work to do to find out whether this thing is differentiable. The derivative would be a little bit of work. Instead, what I can do is I can check to see if this thing is continuous. If this thing, remember, is not continuous at x equals 2, then I know it's not differentiable. That's the contrapositive of this. So let's check continuity at x equals 2. We're going to go back to our definition of continuity. The first part of the definition is you have to show that f of 2 exists. I'll put a little question mark there. Can we show that or not? Well, let's plug in. Oops, it's not f though. Remember, it's function g. So let's find out what g of 2 is equal to. Well, g of 2 in the numerator you get 0. In the denominator you get 0. Uh-oh. So this thing is undefined. And of course, if g of 2 does not exist, then I'm not continuous at x equals 2. And if I'm not continuous, I know I'm not differentiable. So I can make a similar conclusion here. I can say, thus, g of x is not continuous, I'll abbreviate that, at x equals 2. Therefore, g of x is not differentiable. I'll abbreviate that as well, at x equals 2. So I didn't have to find the derivative in this case. I used that contrapositive of my property. If your function is not continuous, then it's not differentiable. All right, let's try one last example here. This time they give us several graphs here. Example 3, it says state whether the function in the figures there below are differentiable or continuous at x equals c. So let's take a look at each of these and then conclude whether they're differentiable or continuous or both. So for the first one here, I can see that the function is continuous. In fact, if we wanted to name this feature in the graph, then remember the feature that we used to describe this is called a cusp in this graph. But I can see that in this case the function is continuous. I'll write that down below here. F of x is continuous. However, when I look at differentiability, remember differentiability means that the derivative exists, which goes back to that limit of a difference quotient. So in other words, if I were to look at the slopes of this graph, if I look at the slopes for the graph to the left of C, I can see, I'm going to just kind of sketch a couple of tangent lines in there. You can see that those tangent lines that I've got sketched there have a negative slope. In fact, they get more and more negative the closer I get to C. So I don't know exactly what the slope is over on the left side of C, but it's some negative number. And over on the right-hand side, if I were to sketch in the slopes over here, I can see that these are some positive slopes. So from the left-hand side, I'm approaching a negative number as far as slope is concerned. From the right-hand side, it's approaching some positive number as far as slope is concerned. So therefore, f of x is not differentiable. And again, if you remember the definition that we had for a cusp was a point on your graph where the function is continuous but not differentiable. So that's just straight from the definition of what a cusp is, that we know that you're going to get continuity but not differentiability at every single cusp that you look at. All right, let's take a look at this next one here at C. So the next one here looks like we have a step discontinuity. And so because of the fact that I have a step discontinuity, I'm not continuous there. I'm not continuous in this case. If you go back to the definition of continuity, it looks like the function exists at C, but the limit does not exist. From one side I'm approaching one value, from the other side I'm approaching a different value. So f of x is not continuous. And remember our second property there, the contrapositive of our first property, said if you're not continuous, that you're not differentiable. So we automatically get f of x is not differentiable then here. Okay. And anytime you have a step discontinuity, you're going to see that same thing happens there. Here we have another discontinuity in this function. For this one at c, function h of x, it says that you've got a removable discontinuity at c. So again, the fact that we've got a discontinuity there, this is h of x, is not continuous. And if you go through the definition of continuity there, the function exists. It's that point up above. The limit exists. That's where that hole in the graph is at. But those two are not equal to each other, so it fails in the third part of the definition of continuity. And of course, again, using that contrapositive we just stated a minute ago, if you're not continuous, then you're not differentiable. So we fail at both of those in that case. And finally, let's look at the last one here. Now, they gave you a little distractor over there at the right in the first quadrant, but notice where C is at. C is over here in the second quadrant on our graph. And so there we have a function that is just simply continuous as it goes from left to right. So f of x is continuous. And you can also see that I can sketch these slopes on this thing here. The slopes as I approach from the left side versus the slopes as I approach from the right side. They are nice and evenly distributed there. They're nice and uniform, so they're approaching the same value there. So you have differentiability there as well. So f of x is differentiable. Here's an example where if you looked at differentiability first, and notice that your function is differentiable, you automatically get continuity with it. Probably it's a little easier there to look for continuity first, though. Anyways, that's that example there. And that is the end of this section for us.